So we can also distinguish when we're doing multi-stage experiments if events are independent of one another or not. So if the outcome of one event has no influence on the outcome of a second event, then we call that independent. A really common example of independent events is flipping a coin. The coin doesn't remember what it was before, what it landed on the previous time, or if we have two coins that we're going to flip. And event 1 is getting a head on the first coin, and event 2 is obtaining a tail on the second coin. These are independent events because the coins are not talking to each other. They're not going to say, well, if I'm heads, then you have to be tails. They are independent of each other. They don't influence one another. So if we think about independent events, then the first flip will result in either a heads or a tails, 1/2 and 1/2. And the second flip is also going to do the same thing, heads or tails in equal probabilities. So you could say, okay, what's the probability of getting a heads, then a heads? It would be 1/2 times 1/2 is 1/4. Now, we can simplify this by saying the probability of independent events E1 and E2, we just multiply the probability together. All right, so let's look at another example. If we have a box that has 11 letters in it, and those letters are given by the letters of the word probability, some of the letters are repeated. So for example, B is in this box twice. So let's say that we're going to draw 4 letters out of the box one by one without replacing them. So we're going to take a letter and then remove it from the box. So what's the probability of getting baby, B-A-B-Y, in that exact order? So we could draw a tree diagram for the possibilities here. It would be a pretty big tree diagram since we're starting with 11, and then the next outcome space would have 10 options from each of the first 11 options, and etc. So we could think about just the branch that leads to the outcome B-A-B-Y. So the branch is going to start with a probability of 2/11ths for drawing a B to begin with, and that's because there are 2 B's in the 11 letters. So there are 2 chips with B on it. And then after we take that B out of the box, there are 10 letters left, and only one of them is an A. So the probability of getting an A for the second letter is now 1/10. Then the probability of getting the B for the second letter, there's 1 B left, and there are only 9 letters left because we removed both the A and the B from our first 2 draws. So there's 1 B and 9 letters, so the probability of getting that second B is 1/9. And then finally, the probability of drawing a Y for that 4th letter, there's 1 chip in there that has a Y on it, and there are 8 letters, so the probability is 1/8. So the total probability is given by multiplying these all together. 2/11ths times 1/10 times 1/9 times 1/8 is 2 out of 7,920. All right, so let's look at this final example where we have 3 boxes, and we're going to take a letter from box 1 and then put it into box 2. Then draw a letter from box 2 and put it in box 3, and finally draw a letter from box 3. So we're interested in the event that we are going to, which letter we're going to get from box 3. So if we want to think about this outcome space, we would probably benefit from a tree diagram. So when we start out, we're going to have our first draw, we have 2 A's and 1 B in that first box. So we could take either an A or a B from box 1 and move it into box 2. So if I draw an A, the probability of that is 2/3 because I have 2 A's and 1 B in that box. And I have 1 B in the box, so the probability of drawing a B from the first box is 1/3. So let's just follow one possible outcome at a time. If we draw an A from the first box and move it to the second box, now we have 2 A's and a B in the second box. So when we draw from the second box, we have either an A or a B. But since we drew an A from the first box and we moved it to the second box, now the probability of getting an A in the second box is 2/3, and the probability of getting a B in the second box is 1/3. And if we draw now an A from the second box and we move it into the third box, then we have A and B in our third box. 2 of those would be A's, 2/5, and 3 of them would be B, 3/5. So if we go backwards one step and say, okay, well, if we instead in the second draw drew a B and moved it, then our third draw we would have probability of getting an A as only 1 out of 5 and probability of getting a B 4 out of 5. So along the outcome where we first draw an A, we can have A, 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 B, A, B, A, A, B, B. But the outcome space, the event, we're only interested in the last letter. Okay, so we can again go back to our original draw and say, all right, well, let's say instead I draw a B. That means that my second draw, I could get an A or a B, but the probability of getting an A is 1/3, and the probability of getting a B is 2/3 now in the second draw. If I draw an A, then the probability on my third draw from the third box of getting an A is 2/5, and the probability of getting a B is 3/5. Or I could have gotten a B on my second draw, and then the probability of getting an A on the second draw, or the third draw, would just be 1/5 and 4/5 of drawing a B. So in this bottom branch, we have a B, an A, then an A, a B, an A, then a B, an A, oh, excuse me, B, a B, then an A, or a B, B, B. And again, we are really only interested in that last draw. All right, so let's look at a nicer picture for this. To think about how we're going to answer the problem. All right, so this is the nicer picture of our tree diagram. It's the same thing, but just drawn a little more neatly. So again, we have each of our draws influenced by what we drew the previous time and moved to the second box. So we can follow the train of each of these possible outcomes and multiply their probabilities together. So the probability of drawing an A, then an A is 2/3 times 2/3 times 2/5, or 8/45. So if we want to know the probability of getting a B as our final draw, that will be this outcome, this outcome, this outcome, this outcome. So to find the probability that we get a B as our final draw, we would find the probabilities of each of these branches of our tree diagram and then sum them together to have 12/45 plus 8/45 plus 3/45 plus 8/45, giving us 31/45. Okay, so one final rule that you may find useful is if we want to have events A and B in a sample space, and the probability of A, I think this should be, is not equal to 0. Then we can find the conditional probability that an event B occurs given that A has occurred by saying the probability of B given that A has happened is the probability that both A and B happen over the probability of A. So if we want to put this into action, then the probability of rolling a 6 on a fair die, if you know that the roll is going to be an even number, then the probability of rolling a 6 and an A is just the probability of rolling a 6 and an even number is 1/6, and the probability of rolling an even is 1/2. So the probability of getting a 6, given that it is an even number, would be 1/3. And that is all I have for you today. So let me know if you have any questions, and good luck.